Hello friends, welcome to engineering tutorial. So here is another question on electric field intensity. So the question is that find the electric field at the center of a uniformly charged semicircular arc of radius A and linear charge density lambda. So here is the semicircular arc ABC. It has a radius A, okay. Let this be the center, okay. This is the radius of the semicircular arc, and it has a linear charge density lambda. So what is linear charge density? We have already discussed about charge distributions, okay. Linear charge distribution, surface charge distribution, volume charge distribution. So linear charge density is, suppose we say that we have a particular length of a conductor, okay, where the total length is L, and this L, this length of the conductor, has a total charge Q, which is uniformly distributed throughout this total length. So here the linear charge density lambda will be Q by L, charge per unit length, that is coulomb per meter. That is the unit of linear charge density lambda, Q by L, total charge by total length of the conductor, okay. The charge is distributed uniformly. So that is what is said here. This semicircular arc, this entire circumference, it has a linear charge density lambda, and we have to find the electric field at this point, okay, O, because of this entire semicircular portion ABC. So we'll be using a integration method to do it. So we'll pick a small portion of this semicircular arc. So let us say we pick this portion, okay, this one, and this much portion we have picked, okay. We have picked this much portion, and let's say here the length of this portion is delta L. This portion length is delta L. Angle is d theta, the angle subtended in between these two points, these two portions, okay. Now the electric field intensity due to this small portion, let it be delta E vector, okay, delta E vector, this one, delta E vector, okay. And this delta E vector, it makes an angle theta with respect to this. So this angle will also be theta, okay. So now because of this small portion delta L having a charge concentrated equal to Q delta L, let's say, the electric field intensity delta E vector, we can write it as 1 by 4 pi epsilon 0 Q delta L, charge concentrated in this small region, small portion of the semicircular arc delta L, by this distance is radius A, okay. This entire, this thing, these two lengths are A, so we'll write it as A square, okay. So we can write the Q delta L as the surface charge density, the linear charge density lambda multiplied with the length delta L by A square. That is the whole point of linear charge density. It means charge per unit length is lambda. Lambda coulomb per meter. Okay, so for delta L meters, charge is lambda into delta L, this much coulombs. Okay, so this is the expression of delta E vector. Now if you see here, this delta E vector, it can be resolved into two components. Okay, it can be resolved into two components. One is delta Ex in the x-axis and delta Ey along the y-axis. Okay, so here delta Ex will be equal to delta E cos theta, delta Ey is equal to delta E sin theta. So here if you just notice, okay, if you notice a little bit, this is a symmetrical structure, the semicircular arc. So here if we pick, let's say, these 2 points, what we want to do is that we want to pick this small point and then combine all these delta L's, dividing this whole entire semicircular structure into small delta L's. Okay, n number of delta L's, then we'll integrate it together. So here when we divide it into small number of delta L's, let's say we picked these two regions, okay, exactly opposite to this. Okay, this one and this one, exactly opposite. So here the resultant electric field will be in this direction. Okay, let's use a different color. Here the resultant electric field will be in this direction. Okay, delta E vector. Okay, then this will also be delta E vector. Why? Because everything is the same length delta L we have taken. So your linear charge density is uniform, so same charge Q delta L, distance is same a square, so everything will be the same. Here also it will be resolved into two components, Ey, which will be in the same direction as this one, and then we'll have delta Ex. So what will happen is that the delta Ex components along the horizontal axis, they will cancel each other out. Okay, they will cancel each other out. Same thing is true for all the small number of elements which are positioned on either side of this axis. Okay, if we divide this whole semicircular arc into two parts, okay, if we divide the whole semicircular arc into two parts, there will be horizontal components of equal values on either side of these axes OB. Okay, so these horizontal components of equal values in opposite directions, they will cancel each other out and will only be left with the vertical components, the Ey components. So this is the only contributing factor, the vertical components, towards the electric field intensity. So the net electric field at point O is equal to the summation of the vertical components or the Y components. So that is equal to summation or integration of 1 by 4 pi epsilon 0 lambda dl by a square. This is the expression that we determined. In place of delta L, now I am writing dl. Okay, lambda dl by a square, and that is sin theta. Okay, sin theta. This is the whole thing. Now you know that the length of an arc, okay, the length of an arc let's say the angle subtended, the central angle is theta, this is the length of the arc and this is the radius. So the length of the arc is equal to r theta, product of the radius and the central angle. So here also this is the central angle d theta, this is the length of the arc dl, delta L is equal to dl, see delta L is the same as dl, okay, don't get confused. So here dl we can write it as a theta, we can write it as a theta, sin theta because only the vertical components are involved. So 1 by 4 pi epsilon 0 dl is equal to a theta, a d theta, okay, dl is equal to a d theta. Here according to this figure, dl, this arc length, is equal to a d theta. A is the radius multiplied with the central angle d theta. So we'll substitute lambda a d theta by a square sine theta from the value of the lower and upper limits of integration will be from 0 to pi because this is a semicircle arc. So here a will get cancelled, this will be a, so it will become lambda by 4 pi epsilon 0 a sin theta d theta from 0 to pi, okay. So it will become lambda by 4 pi epsilon 0 a, this will be minus cos theta from pi to 0, which is equal to lambda, if we take the minus outside, minus lambda by 4 pi epsilon 0 a cos theta, cos pi minus cos 0, which is equal to minus lambda by 4 pi epsilon 0 a minus 1, which is equal to total lambda by 2 pi epsilon 0 a. This is the final value. So the net electric field intensity at point O due to the semicircular arc, okay, the net electric field intensity at point O due to the semicircular arc, the value of magnitude is lambda by 2 pi epsilon 0 a, this lambda by 2 pi epsilon 0 a. So you can remember this formula also. If a numerical type question comes, you can directly put the value. It will be either given the linear charge density value or the radius value. Anyway, any kind of a permutation combination can happen. Any two values will be given, you will have to calculate the third one. So like that it will be given and you can put the value and get the answer. This is a derivation type problem where we had to derive the expression of the electric field intensity due to a uniformly charged semicircular arc at the center, okay, the net electric field intensity at the center, okay.